Welcome to this short presentation by Sono Nerds. We are going to learn today about axial resolution. But first we need to ask, what is resolution? Well, resolution describes the way that detail can be displayed. When we say something has more, better, or higher resolution, it means that it can create a more accurate display. Therefore, higher resolutions are preferred for image accuracy. There are multiple types of resolution that we consider when creating ultrasound images. As you study physics, you will learn more detail about each of these resolutions. But briefly, they include spatial resolution, which is dependent on the pixels of a monitor or the number of scan lines that create an image. Contrast resolution, which is the ability to differentiate between shades of gray. Temporal resolution, that determines the accuracy of moving objects. Elevational resolution, which is going to determine if we are accurately seeing a thin slice of anatomy with an ultrasound beam. Lateral resolution determines the accuracy of side-by-side structures being displayed. And lastly, we have axial resolution, which determines how accurately a system can display two reflectors that are parallel to the sound beam. Axial resolution has a lot of synonyms that it can go by, and you may see these during your testing, and they are going to include longitudinal resolution, radial resolution, range resolution, and depth resolution. These are all synonyms for axial resolution. Now, it bears repeating that the definition of axial resolution is a machine's capability of accurately displaying two reflectors that are parallel to the sound beam. But you might be wondering, what really does it mean to be parallel to the sound beam? When sound beams are emitted from a transducer, the pulse is sent directly from the face of the transducer. The sound beam travels into the body and is going to interact with reflectors. It is the reflectors that are sitting within the length of the pulse or run in the same direction of the pulse that we consider to be parallel to the beam. Another way we can think of this is that these are reflectors that sit in front and back of one another rather than side by side. So axial resolution will determine, can the machine accurately display these reflectors, or will it inaccurately display the reflectors? So what determines axial resolution? What machine parameter decides that the machine will be able to produce those accurate images? Axial resolution is determined by the spatial pulse length. Recall that spatial pulse length is the distance a pulse takes up in space. So if we could get out our tiny little rulers and measure the pulse, we would be able to determine the pulse length and therefore calculate the axial resolution. And yes, I did say calculate, and that is because axial resolution has its own formula. So here it is. We have axial resolution is going to be equal to wavelength times the number of cycles in a pulse, all divided by 2. Now you might be looking at part of that formula and thinking, hey, wavelength times the number of cycles in the pulse is the SPL formula, and you would be absolutely correct. So if it is easier, you can think of axial resolution formula as being spatial pulse length divided by 2. Note that because SPL is in millimeters or a distance, that axial resolution is also in millimeters or a distance. In ultrasound, the common values of axial resolution are from 1 millimeter to 0.1 millimeters. This means that structures must be at least 1 to 1/10 of a millimeter apart to show up separately on the display. Most of the reflectors in the body are just going to be mere millimeters, if not even less, apart, and our ultimate goal in ultrasound is to create the most accurate image of the body as possible. Knowing this, we can confidently say that a low numerical number means that the image displayed is more accurate than a high numerical number when calculating axial resolution. So let's take a look at an example. The beam on the right is made up of a pulse with an SPL of 10 millimeters. Using our axial resolution formula, SPL divided by 2, we can take 10 divided by 2 and calculate the axial resolution to be 5 millimeters. That means that each of these reflectors must be at least 5 millimeters apart to be displayed accurately. When they are not, the machine cannot tell that these are two separate reflectors and will display them as one. Now this is going to occur because the pulses are too long and their echoes from the reflectors are going to overlap. The machine cannot tell that the echoes are overlapping and processes it all as one echo. Let's take a look then at the beam on the left. These pulses have an SPL of 2 millimeters. Using our axial resolution formula again, SPL divided by 2, we can take 2 divided by 2 and calculate the axial resolution to be 1 millimeter. That means now that each of these reflectors must be at least 1 millimeter apart to be displayed accurately. And as long as they meet that minimum distance calculated by axial resolution, they will be displayed as they truly are, 2 separate reflectors. With short pulses, there's enough room for independent pulses to return without overlap and to be processed. So now we can say that axial resolution is going to improve with low numerical values, which improves due to short SPLs. So if we know that low numerical values are better, then how do we adjust the machine to improve the axial resolution? Well, you can't. Axial resolution is not adjustable with a knob on the machine, and that is because spatial pulse length was one of those goofy parameters that is determined by the sound source and the medium. So for ultrasound, that means it is tied to the frequency and manufacturing of the transducer, as well as the soft tissue it travels through. And if it's true for SPL, it's true for axial resolution as well. In fact, there's actually another formula that shows us this. In soft tissue, axial resolution is equal to 0.77 multiplied by the number of cycles in a pulse, all divided by the frequency of the transducer. The 0.77 is referring to 1.54 millimeters per microsecond of travel in soft tissue divided by 2. So now you may be thinking, well, there's not a knob to change the axial resolution, but what if I grab a different frequency transducer? Well, then you're definitely on the right track of how to improve your axial resolution. Let's look back at our formula. Frequency is under the division line, so that means that frequency and axial resolution are inversely related. If we increase the frequency, we are going to decrease the axial resolution value, which is what we want. That's going to improve axial resolution. And it does this because when we increase the frequency, we get shorter wavelengths. When we have shorter wavelengths, we decrease our SPL, and when we decrease our SPL, you guessed it, we decrease the axial resolution distance. High frequencies are going to be more desirable when we want to improve our axial resolution. This is because we will see improved axial resolution with short pulses that are made with short wavelengths from the high frequency transducer. Contrary to this then, low transducer frequencies are going to create long wavelengths, which will increase the length of the pulse, therefore creating poor axial resolution. When imaging, you should always choose the transducer with the highest frequency to improve your resolution, but it also needs to give you enough sound penetration to image to your target anatomy. Okay, so changing the frequency worked. Can we change the number of cycles? Well, yeah, you can, sort of. The number of cycles is above the division line, so it's directly related to axial resolution. If we decrease the number of cycles in a pulse, we will decrease the axial resolution distance. Again, this all comes back full circle to the SPL formula and axial resolution. But the number of cycles is determined by how the transducer is made. Sonographers don't really get a say in this, but the manufacturers thankfully know what they're doing. In imaging transducers, manufacturers are going to add backing material. When there's backing material in a transducer, it causes the transducer to make more of a chirping sound, which produces short pulses rather than a long ringing tone. The reduction in ringing means that there are less cycles within the pulse. Therefore, it will take up less space, making the SPL short, and again, reducing the axial resolution value. When we let the transducer ring, it can make more cycles per pulse, which makes the pulse long and degrades the axial resolution. This is another reason why imaging transducers have backing material to help create short pulses, which improves the resolution. So to recap, axial resolution tells us the minimum that 2 reflectors that are parallel with the beam must be to be displayed accurately. Axial resolution then improves with low numerical values, which are due to short SPLs. Short SPLs come from high frequencies because of the short wavelengths, and fewer cycles, which is caused by less ringing and backing material. So let's go over a few scenarios in which we're comparing situations and we're going to decide which one has the better axial resolution. So a 5 megahertz probe that produces pulses with 3 cycles per pulse, or a 5 megahertz probe that produces pulses with 4 cycles per pulse. Remember, higher frequencies, fewer pulses equals better axial resolution. So in this case, we're going to choose the one with the fewer cycles per pulse because the frequencies are the same. Our next scenario, we've got a 5 megahertz probe that produces pulses with 3 cycles per pulse, or we have a 12 megahertz probe that produces pulses with 3 cycles per pulse. Now in this scenario, the cycles per pulse are the same, but the frequencies have changed. Higher frequencies produce shorter wavelengths, which improve our axial resolution. So we are going to choose the transducer with the higher frequency. We have a pulse with an SPL of 2 millimeters, or we have a pulse with an SPL of 1 millimeter. Calculate both of them. The top one, we get an axial resolution of 1 millimeter. The bottom one, we get an axial resolution of 0.5 millimeters. We know that the lower numerical number is the better axial resolution, so that will be the pulse with the SPL of 1 millimeter. And for our last one, we have a wave with 0.2 millimeters wavelength, or we have a wave with a 0.4 millimeters wavelength. Again, the shorter the wave is, the shorter the SPL. So we want to choose the one that has the shorter wavelength, which will be our 0.2 millimeter. Thank you so much for hanging out with us. Let me know if you have any questions.